For the beam shown below with constant EI by double integration method, determine the slope and deflection at C, at G, which is 8 meters horizontally from A, and at E. So first, let's compute for the reaction at A. So moment D0, clockwise positive, AY times 11, then minus 1 half or 0.5 of 3 times 30, then 1/3 of 3 is 1 plus 4, so 5. So 0.5 of 3 times 30 times 5. Then for this triangular loading, the base is 4, the height is 18, 30 minus 12, 18. Then the moment arm 2/3 of 4, which is 8/3. So minus 0.5 of 4 times 18 times 8/3. Then for this rectangular loading, minus 7 times 12 or 12 times 7, half of 7, 3.5, so this is 0.5. So minus 12 times 7 times 0.5. So solving for AY is equal to 33 kilonewtons. Then let's put it there. AX is 0, not shown. Then let's solve for RD by summing up forces vertical. RY is 0. So 33 plus RD, then minus 0.5 of 3 times 30. This one. Remove the moment arm. Minus 0.5 of 4 times 18. Then minus 12 times 7. So R sub D is equal to 132 kilonewtons. Let's put also there. Then let's have two differential equations, AC then to CE. For the portion AC rather, so let's call that X, then the intensity of this loading W, represented by that yellow intensity. So W as to, this is X minus 4 equals 30 as to 3. 30 as to 3 is 10, so 10 times X minus 4. So that intensity is 30 times X minus 4. Therefore, the differential equation for portion AC, EI y double prime AC, is equal to 33 times X minus 1 half of quantity X minus 4 times 10 times X minus 4, then moment arm X minus 4 over 3. Simplifying, EI y double prime AC is 33X minus 5/3 of quantity X minus 4 cubed. Integrating once, EIY prime AC is 16.5 X squared minus 5 over 12 times X minus 4 raised to 4 plus C sub 1. Take note that when X is 0, Y is 0 at A. So there is no C sub 2. Integrate again. EIY AC is equal to 16.5 over 3 is 5.5 X cubed minus 112 X minus 4 to the 5th plus C sub 1X. Then for the second part, call that X from the left. So let's have CDE for easier differential equation. Then let's consider forces at the right and the loads at the right. So this is 14 minus X. The total length of the beam is 14 meters, then minus X. So therefore, this distance is, let's divide this loading into rectangular and triangular loading. This distance is 11 minus X, that one. Then let's call that W2, this intensity. W2 as to 11 minus X equals 18. 30 minus 12 is 18 as to 4. 18 over 4 is 4.5. Therefore, the intensity of this loading is 4.5 times 11 minus X as shown. So therefore, the differential equation of the elastic curve for portion CE, EI y double prime CE, is 132 times quantity 11 minus x minus 12 times 11 times 14 minus x times 14 minus x over 2, so minus 6 times 14 minus x quantity square, then minus the moment of this triangular loading, 1/2 of 11 minus x times 4.5 times 11 minus x times quantity 11 minus x over 3. Simplifying, EIY double prime CE is equal to 132 times 11 minus x minus 6 times quantity 14 minus x square minus 0.75 of 11 minus x quantity cube. So integrating once, EIY prime CE is negative 66 11 minus x square, negative because this is integral of 11 minus x, take note minus x, then this is positive, divide by 3, so 2 14 minus x cube, then this is again negative of negative because we are integrating 11 minus x quantity cube, so the differential of 11 minus x is negative differential x, so that's why negative 3/4 divided by negative 3/4 times negative, so over 4, so negative of negative, so positive 3 over 16 11 minus x to the 4th plus constant of integration c sub 3. Integrate again, EIYCE equals positive 33 11 minus 22 11 minus x cube, then minus 0.5 2 over 4 14 minus x to the 4th, then minus 3 over 80 3 over 16 over 5, so negative 3 over 80 11 minus x to the 5th plus c sub 3x plus c sub 4. For the boundary condition, when x is 7 11, YCE is 0 or YD is 0, so 0 equals 11 minus 11 0, this is 0, this is negative 0.5 14 minus 11, so 0.5 of 3 to the 4th, this is 0, then plus c sub 3 times 11, then plus c sub 4, so 11 c sub 3 plus c sub 4 equals 40.5. Call that equation 1. Then there's no more boundary condition, but the common point is C for the two differential equations. That means the slope at C when x is 7 is the same. So that is EIY prime AC, this equation here, when x is 7 is equal to EIY prime CE when x is also 7. So substitute 7 here. So 16.5 times 7 square minus 5 over 12 times 3 to the 4th plus c sub 1 is equal to negative 66 times 4 square plus 2 times 7 cube, as long as this is positive inside the parentheses, that's included, plus 3 over 16 4 to the 4th, then plus c sub 3. So setting up c sub 1 minus c sub 3, so c sub 1 minus c sub 3 is equal to negative 1096.75. Call that equation 2. Also, the deflection at C is common for the two equations. That is, EIYEC when x is 7 is equal to EIYCE when x is 7. So 5.5 times 7 cube minus 112 times 3 to the 5th plus c sub 1 times 7 is equal to 22 times 4 cube minus 0.5 times 7 to the 4th minus 3 over 80 times 4 to the 5th plus c sub 3 times 7 plus c sub 4. So c sub 1 minus c sub 3 times 7, then minus c sub 4 is equal to the simplification of these constant terms, negative 6097.15. Substitute the value of c sub 1 minus c sub 3, which is negative 1096.75, into this equation. So negative 1096.75 times 7 minus c sub 4 equals negative 1697.15. So we can now solve C sub 4. C sub 4 is equal to negative 5980.1. Then substitute into equation 1 to solve for C sub 3. So 11 C sub 3 plus negative 5980.1 equals 40.5. So C sub 3 can now be solved. C sub 3 is 3103 over 55. Then substitute into equation 2 to solve for C sub 1. So C sub 1 minus 3103 over 55 equals negative 1096.75. Solving for C sub 1, C sub 1 equals negative 549.423 in decimal. Then we can now compute theta C. Substitute into this equation or into this equation. So let's select this equation. When x is 7, EI theta C is 16.5 times 7 square minus 5 over 12 times 3 to the 4th, then plus C sub 1, which is negative 549.423. So from there, we can solve theta C. Theta C in decimal is 225.327 over EI. Next, into this equation for delta C, x is 7. EI delta C is 5.57 cubed minus 1 over 12 times 3 to the 5th. Then plus C sub 1, which is negative 549.423 times 7. So delta C is equal to negative 1979.711 over EI. Then at G is in portion CE, so we cannot use this equation but rather this equation here. Substitute x is 8, they can solve theta G. So EI theta G is negative 66 times 3 square plus 2 times 6 cube plus 3 over 16 times 3 to the 4th plus C sub 3, which is 3103 over 55. So theta G is equal to 400.515 over EI. Then into this equation, x is 8 to solve for delta G. So EI delta G is equal to 22 times 3 cubed minus 0.5 times 6 to the 4th minus 3 over 80. 11 minus 8 is 3 to the 5th plus C sub 3, which is 3103 over 55 times 8 plus C sub 4, which is negative 5980.1. So solving for delta G is equal to negative 1664.594 over EI. Then finally, at E, when x is 14, to solve for theta E here, so because 11 minus 14 is negative, this is ignored. 14 minus 14 is 0, so that's 0. 11 minus 14 is negative again, ignored. So therefore, EI theta E is C sub 3. So EI theta 3 is C sub 3, and C sub 3 is 3103 over 55. Then let's express that in decimal. Theta E is equal to 547.327 over EI. Then delta E into this equation, x is 14, 11 minus 14, because this is negative, this is ignored. 14 minus 14 is 0. 11 minus 14 is negative again, so that's ignored. So the terms will only be C sub 3 times x, C sub 3 times 14, plus C sub 4. So EI delta E is equal to C sub 3, which is 3103 over 55 times 14, plus C sub 4, which is negative 5980.1. So we can now solve delta E. Delta E is equal to 1682.482 over EI. So that's it for this problem, and the loading is quite challenging, and this is one of the challenging problems in beam deflections.